Thanks everyone for joining today. This is the second joint workshop among our projects. And I will immediately leave the floor to Ainhoa Cortés from, from WILLOW project. Please, Ainhoa, take the floor.
Yes. Let me share because I can't now.
Okay.
Yeah.
You should be able now.
Yeah. Okay. I go. Yeah.
We can see you.
Yeah. Okay. Good morning, everybody. I'm Ainhoa Cortés from SEIT, which is our research institute in the Basque Country, north of Spain. And I'm the coordinator of the WILLOW project. Well, it's my pleasure to be here today. Thank you, everybody, for joining this webinar and for giving me the opportunity of sharing our research in WILLOW project. Today, I'm going to focus on one of the outcomes of this project, in this case, on what we have developed based on ultrasound method for pitting corrosion and coating degradation as consequences of, or measuring the consequences of this kind of problems in offshore wind, okay? So there is a lack of success in implementing decision-making schemes for offshore wind farms where the corrosion has a crucial role. Let's say that we have high degradation rate of structures affecting the remaining useful lifetime of these structures and components which operate in these harsh environments. Then WILLOW aims to develop an open source and data-driven smart containment solution, but taking into account the degradation of the structures in offshore operation and looking for a trade-off between power production and lifetime consumption. Then in WILLOW, we have three main technical objectives, and today we will focus on the first one, which is the design of a global structural health monitoring system based on different physical parameters like loads, accelerations, images, thickness losses, and handling problems like fatigue, pitting corrosion, and coating degradation by the development of physical and virtual sensors combined with machine learning techniques. So specifically, I will talk today about pitting corrosion and coating degradation and how we can estimate or predict these problems using ultrasounds. Then with this aim, SEIT we develop a continuous and in-service monitoring system based on pulse echo ultrasounds using piezoelectric transducers, designing ad hoc electronics and our own signal processing and models to estimate and predict these offshore structures degradations. Then our system is an autonomous system, low cost, low power consumption, because we want to operate during years, 2 or 3 years, having easy deployments. So we integrate in our solution wireless communications and keeping the high accuracy required to detect and quantify pitting or the coating degradation. And without forgetting the high robustness we need to operate in this kind of marine environments. Then, starting with pitting corrosion, we develop our own system. Here in the photos, you can see our sensor nodes. The electronics designed by SEIT is inside these IP housings. Okay, then you can see the signal cable, and here the piezoelectric sensor, the transducer attached with glue to hammer per pitched plates. Okay, then below you can see the gateway we use to collect all the data coming from the sensors. Here we have again the electronics into the IP housing and the supply cable. Then this gateway will collect all the data from the sensor nodes deployed in the structure wirelessly using a short-range communication, in this case ultra-wideband. And then this gateway will send all the collected information to the cloud using 3G or 4G communications. Here in the middle, you can see some figures of the simulations we perform with a K-Wave toolbox in MATLAB to see how the shape of the pit affect the ultrasound reflections. Okay. And on the right side, in these figures, we saw the pit situation, which is the red line, the no pit situation, which is the blue line, and how when we have the pit, we see the attenuation of the signal, loss of power between consecutive echoes, and even a slight echo delay and echo shape change due to the scattering. In fact, here you can see some additional reflection due to the pit wall before the main back wall echo. Here, I have to say that this is not a finished activity. We have several lab experiments ongoing, and the aim of these experiments is to evaluate how the pits grow. Then we are submerging these plates with pre-pitted in stalled water and measuring periodically with ultrasounds and correlating this data with the measurements with a perfilometer and also with electrochemical sensors designed by other WILLOW partners. And that way we can have some kind of reference and characterize the different pits. So the final aim is to propose our algorithms and machine learning models based on the collected data. Apart from the lab testing, we have deployed sensors in a real offshore floating offshore platform. This is in this case, this is the HARS lab in the Basque Country. And here you can see how we installed 3 sensor nodes, the gateway, and also the plates with the transducers in the splash zone. We selected 2 plates, in this case number 1 and number 3, with pit and no pit situations and using different transducers. And the pits are of different diameters and depths. So the idea again is to evaluate how these pits grow in a real environment and correlate those data with the data coming from the lab. In addition to get the data, the idea is also to validate the robustness and the autonomy of our complete system in this harsh environment during 1 year. Okay, related to coating modeling, Said has developed an ultrasound echo-based methodology for estimating coating thickness by first obtaining the impulse response of the test medium through a deconvolution model, and followed by an enhanced detection of coating layer thickness in the reflectivity function using a one-dimensional convolutional neural network, which is trained with synthetic signals generated by K-wave simulations. Then a key objective here was to eliminate the dependency on a reference signal in the deconvolution process. We proposed a novel deconvolution model that operates on 2 consecutive backwall echoes to extract the reflectivity function of the tested medium. Additionally, we applied key changes in the convolutional neural network related mainly to the synthetic signal generation and with the filters inside the architecture of this network, adapting the filters to capture the local overlap patterns across the wide range of coating thicknesses in our dataset. The idea was to detect closely spaced reflected impulses within the reflectivity function. So finally, we achieved this hybrid framework that integrates the deconvolution model with a convolutional neural network for this coating thickness estimation. And if you want to go for more detail, you can check this our recent scientific publication. Okay, and here some results. Okay, on the left, you can see the received signal and how the overlap causes partial amplitude cancellation due to the overlapping reflections produced by the coatings. Then these additional reverberations within both coatings create oscillations that make it difficult to extract the actual ground truth visually or with conventional signal processing method. That's why we implemented the convolutional neural network, which can learn the local patterns corresponding to the small differences in peak amplitude, spacing, and oscillation frequency between the still backwall and front coating backwall reflection. Thus, it allows the extraction of the spice corresponding to the reflectivity function with higher accuracy, as can be seen here on the right side in the predictions for different coated thicknesses and obtaining small precision errors. Okay. And to finalize, some conclusions related to pitting evaluation. Okay, we saw that sensor resolution and sensor beam diameter are key to detect the pit effect. In fact, if we want to see some effect in the ultrasound signal, we need a ratio bigger than 0.2 between pit diameter and sensor beam diameter. And for solo pits, which is the initial stage of the pitting, we need high frequency transducers. Related to pit shape, when you use transducers which send longitudinal waves, which is our case, most of the signal power that does not reflect back perpendicularly is lost. If the back of the pit is flat, then we can capture its reflection. If not, we need to focus on other parameters, on other effects like attenuation or decay rate between the energy of consecutive echoes to see how much signal is scattered away due to the pit. And related to coating modeling, we developed the novel convolutional neural network enhanced ultrasound echo-based deconvolution model to estimate front-side coating thickness in 3-layer coated steel samples. And well, we achieved a method to remove the dependency on the incident ultrasound pulse by the convolving 2 consecutive backwall echoes and being able to estimate the reflectivity function of the 2 main interfaces of interest, the steel front coating interface and the front coating air interface. We generated synthetic signals from known coating properties using the elastic simulations, and we trained the network with these synthetic signals. We designed one-dimensional convolutional neural network to discriminate the reflections of the stick backwall and the front coating backwall. And our model can predict accurately coating thicknesses between 60 and 740 micrometers with a thickness prediction mean accuracy of around plus minus 0.8 samples, which is around 8 micrometers. And this is all from my side. Thank you very much for your attention. I hope that it was for your interest. And if you have any question, please, I'm here to answer.
Hello, from the chat, I don't see any questions, but please make your questions. So I think we can pass the floor to the next speaker.
Okay. I remember that we also have at the end of our workshop a 10-quarter-hour Q&A session, so you can do your question later. So I give the floor to Vasilis Pettas from TWAIN project. Vasily, now you should be able to share your screen.
Hello.
Oh, thank you.
Can you hear me?
Yes.
Yes. It works, the sharing?
Yes.
Okay.
Please go ahead.
So, hello everyone. My name is Vasilis Pettas. I'm a postdoc at DTU Wind Energy. And today I want to present the work we did within the TWAIN project regarding the effects of bat protection strategies on energy production and structural loads of wind farms. This work is done in collaboration with my colleague Tuffe from DTU and also Thomas Duck from NG Green and Andreas Vad and Antonina Vurkobat from Technical University of Munich. So to start with, we all know that bat protection is necessary but can also be costly. Bats are vulnerable to wind turbine collisions, and in order to mitigate the environmental impact, operators try to reduce these effects, but also legally required to meet specific regulations for specific species and different regulations on local and regional level. So most bat protection that exists today reduce energy production and affect the turbine loading potentially due to the more frequent shutdowns. But this is something that is not quantified properly. And the aim of the work we do in the TWAIN project is in order to guide an efficient decision-making on how to approach better the bat protection strategies, to find a way and suggest a method to quantify these trade-offs. Before I continue, I want to explain a bit what are these bat protection strategies that we consider and the most widely used. So first is a static or blanket control, as it's called. In this case, the shutdown of the turbines is triggered by predefined environmental threshold. When these thresholds are met, then the wind turbines are shutting down. These thresholds are derived in the pre-construction phase by experts, where based on the flora and fauna of the region, they can identify variables such as wind speed, temperature, humidity, precipitation, also dates, time of the day, that define these thresholds, which are tunable to different protection levels. So we can have like 90, 99, 100% protection levels, etc. The other approach is a dynamic control, where the shutdowns of the wind turbines are triggered by real-time bat protection using acoustic or image sensors. And then the turbines shut down for a predefined duration when activity is detected only. So this assumes an ideal sensor coverage, and it's considered 100%. This is more novel approach, while the most common approach now in the field is the blanket control. So in the work we are doing within TWAIN, we want to develop a data-driven framework that enables us to evaluate the impact of these bat protection strategies on the wind farm performance. And for this particular study, we used data from an onshore wind farm in France to run a case study and identify these trade-offs. So now I will say a few words about the methodology we used to create this framework. To begin with, I want to show some figures on the correlation of environmental patterns and bat activity, so that we can have a better understanding of the activity patterns of bats. So bats are detected when wind speeds are relatively low. As you see here, this is the distribution of bat activity as measured by a sensor there in the field for 2 years. And we can see that bats mainly appear in wind speeds below 8 meters per second, so closer to the cut-in and in region 2. Then they appear when it's not too cold, so they above 13 or 14 degrees Celsius. And then they are nocturnal birds, so they appear at night and mainly in summer months. So based on this, we can understand how one could derive these environmental thresholds based on more data from multiple years and be able to identify protection levels based on these thresholds. Then I want to talk about the evaluation framework we developed. In a conceptual level, the evaluation framework starts with ambient conditions. So we get wind speed, wind direction, TI from the site in an ambient level, and also bat activity data. Then for each time block, we apply this bat control and define the operational state of the turbine, which can be normal production, starting, stopping, or idling. Then we are using the Floris in order, which is a software for identifying the flow of waked fields in a farm, where we feed the environmental conditions, the ambient conditions, and we get the local inflow for each of the turbines. Then we feed that to a trained load surrogate based on our elastic simulation. So at each time step, we can get the damage equivalent loads. So we can loop over a long time series, and then we can accumulate the DLs, all energy production, revenue, or other KPIs over time to give a cumulative value. And thus, we can compare the different cases. A few more details on the modeling. So we use a site-specific calibration from Floris to account for terrain effects and speed-up factors based on the method developed by our colleagues in TUM. And then we use the IA 3.4 model for simulations, as we didn't have the actual wind turbine, but it's very close in terms of dimension and capacity with the actual wind farm model. And then we use HOC2 simulations for different cases, normal operation, idling, startup, and shutdown, 10 minutes, in order to create a database for training. Then the surrogate model has as input the rotor effective wind speed, the rotor effective turbulence density, and the operational mode, the 4 modes I mentioned. And the output is the 1 Hertz damage equivalent load and the energy, for example. We tested different methods. Due to the small data set, it seems that the piecewise spline interpolation behaves better. Here you can see the error between the test set and the trained model, but also we have a neural network model and a Gaussian process regression model that I will not show today. And the bat control then is applied over time, and we have a state machine which changes the transition of the state of the wind turbine, being either idling, then it starts, then it's in normal operation. So it imitates the normal behavior of the wind turbine. DLs are converted based on magnitude damage, and so we can get the cumulative values over time. And the energy production in this case is calculated by Floris. So the case we want to simulate, the first case is the baseline case, where we have no bat protection strategy, and we want to just running as a reference point in order to compare the next strategies. The first strategy is the static bat control. We are based on the data we got from the experts from the company. We have the protection levels for 90, 99, and 100% based on temperature, wind speed, and date only. And of course, based on night time. The duration of an event of shutdown is dictated by the environmental condition only in this case. In the second case, we used the data measured with acoustic sensors, which assumes 100% protection, and we only stop the wind turbines when the activity is detected with this 10-minute interval. The stop duration, we decided to test 2 cases, one that is only for 10 minutes stopped when the bat appears, and when it's considered a 30-minute stop. The environmental data extracted from the SCADA data and patched with ERA 5 from an onshore wind farm in France, and the bat activity is recorded for 2 years, but the studies for one of the 2 years based on a sonic sensor mounted on one of the turbines. The assumption is that one turbine sensor is considered representative for the entire farm, and that besides bat control, we don't have other curtailment or shutdowns, for example, for maintenance or for grid curtailment. And that all turbines of the farm start and stop simultaneously. So I want to share some results now, preliminary, which we plan to publish in the next weeks. So here you see for each of the wind turbines, the x-axis is the turbine index, and the y-axis the relative difference to the baseline. So you see the different cases, the static and the dynamic case. What we can see here is that the effect of the duration, of the amount of starts and the duration are kind of competing. So the more starts and stops we have, it increases the loads, but the longer the stops are, this offsets the increase in load. So you can see how, for example, in the flap-wise bending moment loads or fatigue accumulation, we have an increase as we decrease we increase the level of protection from 90, 99 to 100, while the opposite is observed in the TWAIN. This is the trade-off I mentioned earlier. And also, you can see for the energy production, the difference between the different cases in the lower plot. I will show this cumulative in the next plot. I just wanted to show the differences also between the different turbines due to the wake effects that we have. So now I want to show the condensed results combining all the wind turbines. So here is again similar plots. You see the different load sensors plus the revenue plus the energy plot, where we have the relative difference to the baselines, the y-axis, and the scatter you see in the block is the bar plot of the box plot of all the turbines, so all 13 turbines of the wind farm. Looking in the static cases, we see that the effect I mentioned earlier. So in 100%, we have very long stops, which means there is a lower decrease in fatigue or less impact on fatigue when we have increase. While when we go to lower thresholds, this changes due to the more frequent stops. This also, of course, reflects to the energy that you can see in the bottom right, where we start with the 0.4% for static 90 case, while the 99, for example, which is the one used actually now by the industry, is about 1.7% energy loss. And when we go, if we wanted to have 100% protection, we go to a very big penalty on energy, which is about 9%. When we look at the dynamic, we see a different pattern, where in the dynamic case, we have more often starts and stops, which means translates to higher fatigue increases, and but also comes to a lower penalty in energy that you see with a 10-minute stop with a dynamic case, we have about the same energy loss with a static 90 case. While when we increase to 30 minutes the interval, the stop interval, then we have a reduction of about 0.8% AP, but less effect on the loads. So these trade-offs can guide us to choose which method is more suitable for the site, given the amount of bad activity, the cost of implementation, and other topics. For more details, I will refer you to the paper we're going to publish, where we analyze more this effect and these trade-offs and the amount of start and stops and the trade-offs in loads and revenue. So coming to the conclusion and outlook, I want to say again that we created this data-driven framework that is able to realistically evaluate the effect of back protection strategies, including a wake, aware, and laid-out agnostic inflow model combined with a load surrogate model. And regarding the comparison for the dynamic and static cases, we see that static cases, static or blanket control strategies reduce AP more, while the dynamic strategies have a higher impact on loads. For the specific side we investigated in France, we see that both bad protection have a small impact on fatigue load, and probably the decision making will be on the economic level. Although this cannot be generalized, as it depends on the amount of the specific site, the amount of bad activity, and the conditions where the starts and stop happen. For an outlook, what we want to continue doing in the TWAIN projects is to investigate the partial shutdown, where multiple sensors exist in the wind farm and only part of it shuts down when bats are detected, and also to evaluate as a next step whether wind farm flow control can offset this impact. So applying some control strategies to increase AP, whether we can somehow offset this reduction we get from applying the bat strategies. So with this, I want to thank everyone, and I'm happy to get questions and discuss more on the topic with you.
Hello, we have a question in the chat. Do we make the question now or at the end in the Q&A question?
Now, please.
Now. Okay, we have a question. Yerika Lamas thanks the presenter for the presentation and said, you have mentioned that the cost related to bat protection is quite high. Do you have an estimation of how much it is the maintenance cost due to bat events, including the shutdown cost versus the cost related to bat protection?
So I guess the question refers to the dynamic control, where the costs come from implementing and maintaining the systems, the detection systems. And this, I don't have a number and what is how much it costs. We got from different manufacturers, different operators, different cost levels, so I cannot generalize. But in general, when we have a static control, the cost is minimal because it's only the team that updates these thresholds. But when we have dynamic control, one has to consider the reduction in AP and the cost of implementing the system and maintaining it. And in terms of loads, the cost can be quantified only in terms of lifetime loss or lifetime extension capability. The case we showed now seems to be very marginal, close to 3% difference in fatigue accumulation.
Okay, thank you.
No, thank you very much.
Okay, any other question? I cannot see. Again, you will have time at the end of our presentation. Thank you again, Vasilis. Very, very interesting. So I will leave the floor to Xiaowei Zhao from Iconic Project.
Thank you. Can you give me the access to sharing?
Yes, now you should be able.
Yes. Can you see my screen?
Yes, we can see your screen.
Okay, thank you very much, Giacomo. Good morning, everyone. My name is Xiaowei Zhao, a Scientific Coordinator of Iconic. I'm Professor of Control Engineering at the University of Warwick, Director of the UK Cybergen Network Plus in AI for Renewable Energy, and a co-director of the Cybergen Offshore Renewable Energy Hub. Today, I'm delighted to introduce Iolus, an innovation in intelligent wind farm operation by cutting-edge AI. Iolus is the outcome of my team's work in the field of wind energy for the past few years. With the Iconic project, make a significant contribution to its development. The name of Iolus combines AI with Aeolus, the Greek god of wind, reflecting our ambition to revolutionize wind energy through advanced artificial intelligence. First, I would like to give a quick background introduction. We all know that the growth of wind energy is really astonishing. However, scaling up alone on capacity cannot unlock the full potential of wind energy. There are two layers of loss value in many wind farms. At farm level, turbines behave like strangers. Each turbine controller makes decisions in a silo. Same rules set for every site every day. Weak effects can lead to a huge losses in annual energy productions. And at the turbine level, factory set control curves and the parameters are only a starting point. A range of factors, including site-specific wind profiles, gearbox aging, blade wear, and local turbulence, steadily pull those curves away from their defaults and silently shaving off even more annual energy production. Put the farm level and turbine level gaps together, and a sizable slice of wind farm performance is still waiting to be unlocked. And this is where Iolus steps in. So the aim of Iolus is to improving operational efficiency by up to 5%. This boosts output from existing wind farm without new constructions. Here, taking the UK as an example, based on an official 2030 UK government wind energy targets, this improvement in performance is equivalent to adding 3.7 gigawatts of virtual wind farm for the UK. And to physically build this capacity would cost around 7.45 billion pounds. Another way of looking at this is that it would lead to an annual reduction of 4.58 million tons of CO2 emissions based on the 2030 UK capacity. The scheme has taken over 900,000 cars off the road. When extended across the European Union, where the total wind capacity is many times greater, the potential impact becomes even more substantial, represent tens of gigawatts of virtual capacity and tens of million tons of CO2 saving annually. So the core of the Aeolus is a two-layer control system, both driven by machine learning. Particularly, FarmWise achieve whole farm AI control to mitigate weak effects. It's like a real-time farm brain that coordinates the whole farm behavior and maximize the overall power generation. While the turbine is an edge level machine learning fine-tuned engine aiming to optimize the control setting and the parameters of each individual turbine. As part of our validation, we conducted a wind tunnel test in Milan for AI-driven wind farm control. Here is a video from those tests conducted in November last year. Sorry, Giacomo, can you hear the sound?
Yes.
Okay, when we did this wind tunnel test, we booked 5 working days. We thought we might need 4.5 days to do this debugging and tuning of our controller and use half day to collect data. Actually, our controller worked immediately in the first morning. So the AI is much more powerful than we thought. In addition to FarmWise and TurbineEase, Aeolus also has 3 supporting modules, including Coolwind, a GPU-accelerated high-fidelity simulation, FlowFarmer, AI plus CFD hybrid modeling, and WindTwin, AI-powered digital twin for wind farm flow fields. I will briefly introduce each of them. Coolwind leverages the GPU computation to radically reduce the cost of high-fidelity wind flow simulations. For example, in a case study, it can complete a simulation in just 8 GPU hours compared to the 15,000 CPU hours that would be required by traditional methods. The simulation results are demonstrated by the video here. Built on this, FlowFarmer further boosts simulation efficiency by integrating AI with computational fluid dynamics, improving the speed of wind farm simulation by more than 1,000-fold. So this can achieve the real-time simulation based on a laptop. It uses a transformer architecture to enable fast, control-oriented modeling and simulation. Our system also including a digital twin called the wind twin. Wind twin is the first ever digital twin for wind farm flow system powered by physically informed machine learning. It acts as a live mirror, a real-time virtual replica of the wind farm's three-dimensional wind flow, continuously updated with live data. The black dots represent ladder measurements in the front of a wind turbine. These paired videos show the close agreement between the ground truth and the digital twin results. The core function of wind twin is to infer detailed wind flow information from sparse measurement, enabling enhanced control and predictive maintenance. Another case study is this time for the sea power wind farm in the North Sea, demonstrate how our digital twin accurately infer a very large three-dimensional wind flow from only sparse measurement. Moreover, our technology is transferable and can be extended, for example, to create a digital twin for large-scale weather systems. Here, it is reflecting the wind pattern across the whole North Sea. You can see the Aeolus is a holistic system built on three core pillars: control, digital twin, and modeling. Each has been rigorously validated, and together they form a seamless AI-powered wind farm management systems. To summarize, Aeolus is built on a stack of cutting-edge method. It has three core building blocks: modeling, digital twins, and the control system, with the control as a core of it. Aeolus received the inaugural Manchester Finalist Prize, a prestigious award by the UK government recognizing the most cutting-edge AI technology developed for the public good. During the competition, we successfully passed a very comprehensive technical validation conducted by independent third-party companies, which confirm the technological maturity of Aeolus and its enormous potential impact. Also, a high-level judging panel highlights Aeolus as a highly innovative solution that address a critical real-world challenge with significant implications. They also notice that Aeolus has a substantial market potential on a global scale. In addition, Aeolus successfully passed a rigorous ethics and responsible AI assessment led by the government. An important ongoing activity within Aeolus is field testing. As part of the Iconic project, we are currently in the final stages prepare for a field trial in collaboration with the Sea Power Wind Farm in Belgium. We expect to begin the farm control tests next month. And finally, as a closing part of my presentation today, I would like to show you a promotional video for Aeolus, which was produced by the UK Government Department for Science, Innovation and Technology at my lab.
So what we're doing with the Aeolus is actually teaching the AI how to play the wind farm game, how to operate the turbines most efficiently, how to keep them safe, and how to maximize benefit for society.
And by applying the AI systems that we've created, we're optimizing the power generation that we're getting.
Aeolus will have a massive real-world impact that people will actually feel in their daily lives. Instead of just building more turbines, Aeolus helps to get more energy from the wind farms we already have.
At the core of ALIS is its smart control technology, which is then supported by the modeling and digital twin, all powered by cutting-edge AI.
It increases wind farm efficiency by at least 5%. That's equivalent to powering 1.25 million homes every year with clean, free electricity. In 5 years' time, we believe we can be deployed on hundreds of wind farms around the world. Perhaps most importantly, we'll be able to have tailored bespoke solutions for every turbine model and manufacturer, helping wind energy scale faster, cut cost, and become even more reliable.
Thank you very much for your attention.
Thank you. I think, is there any question? No? Okay, maybe we can give the floor to, thank you again, Professor Zhao, and I will give the floor to Professor Jan Willem van Wingerden from SUDOCO project. I should, okay, now you should be able to share your screen. Okay, yes, I can see, yes.
So thank you, Giacomo, for the introduction. And thank you also for the other speakers in this webinar, especially the last one, which has a huge overlap what I'm going to present today. So I'm going to talk about the control room of the future, which is part of the SUDOCO project. And today I will focus on multi-strategy wind farm flow control. So my name is Jan Willem van Wingerden. I'm a full professor at Delft University of Technology and also coming from a control department, as also the last speaker. I also want to acknowledge that most of the slides that I will present today are made by one of my PhD students called Matteo Parigio. So let's start. So the main concept behind the SUDOCO project is to develop the control room of the future. And of course, also here, the big engine is AI. So what you see here in the blue box, is the control room of the future. And this control room of the future will take decisions based on time-varying environmental conditions and also time-varying market conditions. And then we have the ability to turn on or off some of these control technologies, such as induction control, I'll introduce in a second, wake steering, and more novel dynamic induction type of controllers. So the question is basically, when do you turn which module on or off? And of course, there's always a trade-off. Do you want to maximize power? You don't always want to maximize power. You also have the trade-off with respect to loads. And also there are other objective functions like cost of valued energy or OPEX or daily revenue. Now then you can also include other devices, going to hybrid power plants, solar, hydrogen or battery storage. So in today's talk, I will focus on multi-strategy wind farm flow control, and I will particularly focus on the combination of wake steering, a well-known technique, with dynamic induction control, which is a wake mixing technology. So let's go one step back to introduce these two flow control concepts in a second. But first, I would like to again stress that typically when you do wind farm flow control, it doesn't, you don't have a single objective, you have multiple objectives. So today we also look at the objective of power maximization, so maximizing the yield. Please note that there's a minus sign in front of this. And there's always a trade-off. How are you going to load your turbines? How do you make sure that you also have a lifetime of at least 20 years? So in the SUDOCO project, we're also trying to develop these Pareto curves. So the trade-off between loads and yield. And later on in the project, we will do co-design, designing a wind farm in combination with advanced control to also change these lines. So going from a Pareto curve that you see here in green to the one in blue. So at the end of today's talk, you also see a Pareto curve if we talk about multi-strategy wind farm flow control. But first, let's have a look again at these flow control technologies. So I already mentioned induction control. So in the movie at the left, you see an illustration of induction control. So what is induction control? So you basically derate some of the turbines in your farm. Let's go back. You derate some of the turbines in your farm. And then you hope that the energy that you let go will be picked up by downstream turbines. Now, we have seen in field experiments and also high fidelity simulations that this technology doesn't work. At the other side, you have wake steering, which is nowadays a proven technology. And in wake steering, you try to deflect the wake away from downstream turbines. And this is now already part of a commercial product within industry. So that is wake steering. So wake steering is successful. I mean, it exists already for years. We also co-developed together with Anwell the Flores model, which was already mentioned in the second presentation today. And what you nicely see with wake steering is that you deflect the wake away from downstream turbines. But you can also imagine that if you have larger farms, that still this wake is hitting other turbines in the farm. So please remember that statement. If we go to more advanced techniques such as the wake steering techniques, so I call them modern strategies, they are based on destroying the wake. So one of them is called dynamic induction control. So what you do is you basically make the wake bigger, smaller, bigger, smaller. So in 3D, you get a pulse effect. And the idea is to destroy the wake, to get faster wake recovery. An innovation from the TU Delft is the helix. And with the helix, what we do is we basically create a helix shape in the wake, again, with the goal to shorten the wake. Now, what is the effect of the dynamic induction control and the helix on a wake is again shown in the next animation. So here at the left, you see a regular wake. So this is an LES simulation, high fidelity simulation with uniform inflow. And here you see the effect of the so-called dynamic induction control, but also labeled as the pulse. So what you get is wake mixing. The downside of the pulse is that you have huge thrust variations, so also power fluctuations on the first turbine. So what is the real advantage of the helix? The helix, you get the spiral shape, the helix shape in the wake, and the power of the first turbine is constant, although it's losing a little bit compared to baseline. But the big effect of these modern techniques is that you get mixing. And if you put a turbine in the wake, as you can see over here, you get more energy out of a wind farm. So these are techniques that we already presented before the start of SUDOCO. The question that we now put on the table is, when do you want to use wake steering, and when do you want to use modern techniques such as the helix? So to summarize some of the things I just stated, some challenges with going to the next slide. So the challenges I just stated, when do you do wake mixing, right, with the helix, and when do you do wake steering? Or do you want to have a combination of the two? Do you want to have a multi-strategy? The other question, how does it really work for large wind farms? So when I go back to the case of wake steering, where we had nicely 9 turbines, you saw that wake steering was working, but you still deflect the wake away from downstream turbines, and they can still hit turbines further in the farm. The third one is, of course, this becomes a big optimization problem. So how do you solve this? Of course, the solution here is also using AI. And finally, how does it work when there is some uncertainty? Because you can have power gains of 5%, but what happens if reality is different compared to your model? So these are the 4 questions I'm going to answer in the remainder of today's presentation. So what do? We have to develop engineering models. So for engineering models, they already exist for wake steering. So you have Flores, or you have the models in PyWake. In this case, we're using PyWake. In the SUDOCO project, we developed also engineering models for the Helix. So they are now part of the PyWake package, where you can now also say, okay, we would like to have the Helix active. So the wake mixing strategy. And what's nice about engineering models is that you really can test them on larger wind farms. And in this case, we're going to look at the Hollandse Kust Noord wind farm, which is a relatively novel wind farm at the North Sea here in front of the coast in the Netherlands. For the optimization, we developed a new strategy based on the serial refine method developed by NREL, but now with a multi-strategy and also generalized for different objective functions, not only for power, but you can also add other objective functions. Today we also have, for instance, the cost of actuation can be included as a measure or a surrogate for loads. So if you do this for HKN and then you optimize for Helix and wake steering, then you get certain results, but you also have to take wind direction and uncertainty into account. So the wind direction is always varying. It's a dynamic effect. So what we also do is we optimize under uncertainty. And yes, the amount of uncertainty is defined by the standard deviation sigma, which can be 0, but can also be higher numbers like 2.5 and 5. And it represents the amount of wind direction uncertainty. So if we then look at the results, if we go to HKN, so this is the layout of the wind farm, and the dominant wind direction is from the bottom left of my screen. So basically from here, then you can optimize this multi-strategy approach using the tool chain I just introduced and developed within the SUDOCO project. So if you then look at the result, then you get something like this. So what do we see here? So here at the left, you see the annual energy production gain with respect to baseline. And the first 3 columns are related to single uncertainty, so no uncertainty at all. Then the black line is the multi-strategy approach, when you combine wake steering with the Helix. So then you have a gain of around 2% under realistic conditions. Then the second one, let's call it the blue one, is only wake steering, and the last one is the Helix. So in this case, you see that multi-strategy outperforms the other 2, which I think is positive, which is a sign that multi-strategy will work. But you also see that wake steering alone outperforms the Helix. But this changes a lot if you take wind speed uncertainty into account. So then you really see that the effect of wake steering drops significantly for this particular wind farm and the model that we used. And while the Helix is more robust from that point of view, but you always see that multi-strategy outperforms a single objective. Now, how can this be explained? If you do wake steering, you deflect the wake away from the first downstream turbine, but it can still hit other downstream turbines. In the case of the Helix, you basically make the wake shorter. So it's not really sensitive with respect to wind direction variations. And I think that's one of the big advantages of these wake mixing strategies. So if we look at more detail, and then we go again back to the control room of the future, where we can put control strategies on, off, and we can have multiple objectives. So what you now see at the left, you see that we turn wake steering on, and the only objective is to maximize the power of the HKN wind farm. What you see at the right-hand side is then the control strategy that you get on the turbine indicated here with the red star. So the control strategy that you get is that you do wake steering either to the left or to the right for certain directions. So that's what you see here. And for some directions, you do nothing. Right? So you get some kind of control policy on the turbine. And you get this for every turbine. If we now go for the helix, so now I turned off wake steering, I turn on the helix in our control room of the future, and then you see that on this turbine, you always, for this particular angle, where it's also the dominant wind direction, you want to put the helix on with the maximum amplitude. In this case, it's limited to 5 degrees, which is academic. I will come back to that in a second. The interesting thing is, of course, what happens if you combine the two. And there you see that for the dominant wind direction of the windrows, there you want to do the helix, and outside you want to do wake steering. Now, this is for a particular turbine in the farm. You can also do it for other turbines in the farm. So if you now pick a turbine in the middle, you get this one. So what you see in this picture is that there is a lot of control activity, right? So the controller is always active, the pitch amplitudes, or you're continuously pitching or wake steering. So what you can also do is put a penalty on the amount of control effort, right? So the multi-objective aspect. And what we now basically did as an example is we looked into the control effort. So if we also put a penalty on the control effort, so multiple objectives, then you get something like this, right? So this is for a certain weighting for the control effort, but of course you can have all these kind of combinations between power and loads. And if you take a look at all these combinations about control effort and power, you can construct a Pareto curve, where I also started my presentation with. So if you don't look at the Pareto curve, then we see multiple lines, but first let's explain this picture. So on the x-axis, you see the annual energy production gain, and on the y-axis, you see with a minus sign in front, the control effort. So if you don't have any control effort, right, then there's also no gain because the turbine is doing nothing. If you have a lot of control effort, this is basically the maximum that you can do, you end up in the kind of the solid black line, which is the combined strategy with the maximum pitch angle of 5 degrees, you get this nice Pareto curve. So the gain that you get depends also on the amount of control effort that you allow. So again, the black one is the combined strategy. The wake steering strategy is the one that you see over here. And then we have the helix strategy by itself, which is the pink reddish one. And then there are 2 dotted ones, and that's where we also reduce the amplitude of the helix. So instead of having 5 degrees as maximum angle, we do 2.5, which is more realistic if you look at the loads on, for instance, the pitch bearings. So still you see that the combined strategy with 2.5, so that's the black one over here, outperforms wake steering or helix by itself. So you really nicely see here the trade-off, and of course it's up to the operator to set, hey, where do I want to be on this Pareto? So to summarize, conclusions, we are working on the control room of the future and looking into trade-offs, right? So we would like to visualize these trade-offs for operators in the control room. You see that multi-strategy seems to be the optimum. And depending on the amount of uncertainty, it's more wake steering or more wake mixing. And what you also see, if you go to larger wind farms, the helix is benefits compared to wake steering if you compare it with just the canonical cases with 1 or 2 turbines, or 2 or 3 turbines. One doesn't make sense, because of the fact that wake steering, you deflect the wake, and with the helix, the wake becomes shorter. Then the other thing is, if you look into uncertainty, if you have a lot of uncertainty, again, then the helix or wake mixing becomes better compared to wake steering. But if there is no uncertainty, then wake steering works better. And finally, what's next? If you now can do this, right? If you can do multi-strategy control design for these type of wind farms, can we also look at co-design, right? Can we also do a different layout of the wind farm, taking into account advanced control strategies? And are there other strategies, right? So in this case, I focused on wake steering and the helix, but you also have this pulse type of wake mixing, and there are other strategies out there. And of course, you can again also look into induction control for large wind farms. That is where I would like to stop today's presentation, but we're making steps towards the control room of the future. And I think also the future is multi-strategy. So thank you very much for your attention.
Thank you, thank you. And we have a question in the chat.
Yes, we have. David asked, for wake steering and helix, what is the load, the life effect on the wind turbine carrying out the yaw pitching action? For example, for wake steering, the turbine is operating far out of its design certification specification, plus minus 8 degrees yaw.
Yes. So I can refer to a couple of papers that we have written about the loads for the helix and for wake steering. And again, it's important to have the trade-off. So the loads are definitely going up for the helix. For wake steering, it depends a little bit if you do positive or negative wake steering. But it will go up, but you don't turn the helix or wake steering on full time. So I would like to refer to some of our papers where we look into the loading with respect to these kind of advanced flow control technologies.
Thank you. Any other question? You can open your microphone and just ask, I would say to Professor Van Wingerden, but to the other presenter as well. You just need to break the ice.
We have another question. Thank you very much for your presentation. In practical implementation, can I ask, are there any potential ways that the helix approach can potentially overcome operational and maintenance approval barriers, since it needs to apply additional pitch control signals?
So again, right, so a normal turbine can do individual pitch control, and typically it's for load mitigation. If you do the helix, then the loads on the turbines will go up. But we did all these load calculations for the helix. I can again refer to some of the papers that we published. And you only turn the helix on in situations where there is full wake overlap, right? So I also showed you some of these pictures. So in the total time of operation, you turn the helix on approximately like 5% of the time. So does it work for every commercial turbine at the moment? No, you really have to look into the loads of the pitch system. But we're working on that.
Thank you again. We still have time for question, even direct question, if you don't want to write them in the chat, but just ask directly to our speaker. Please open your microphone and do the question directly if you want. In the meantime, Anna shared in the chat the link to all the project website, and I suggest you to subscribe to the newsletters from the project to stay updated. No other question? Okay, I would say that there's no other question. Anyway, you can always contact presenters through the website. So thanks again to all the speakers and to all the attendees for joining us today. This is the second workshop, so hopefully there will be another one in a few months. So thanks again, and good luck with your job. It's very interesting. Today we have dealt with AI, but so biodiversity and a lot of different issues and topics. So again, thank you, and we will close the session. Thank you. Bye.
Thank you very much.
Bye.
Bye.
Thank you. Bye bye.
Thank you.